So this is another advanced higher chemistry video, and this is continuing on our set of videos on experimental determination of structure. And the technique we're going to be looking at in this video is known as mass spectrometry, which is shortened usually to MS. Now, mass spectrometry as a technique is typically used to help you find the GFM of a compound, but it can also give you information about the way that that molecule might break apart into fragments. So certain structural features such as a CH3 group, an OH group, the carboxyl group, things like that. Now, mass spectrometry starts off with your molecule intact, and during the technique it fires really high energy electrons to generate positive ions. So what these high energy electrons do is they knock out other electrons within the molecules, making the molecules positively charged. And then once the molecules have a positive charge, they can be separated using magnets. And they will separate based on their mass, because heavier fragments will be harder to move using a magnet than a lighter molecule. More specifically, we would say that they get separated based on their mass to charge ratio, and we use a small m for mass and we use a small z for charge, so m/z ratio. So the mass spectrometer, we have a sample where we vaporize our compound, we fire these high energy electrons, then they get sped up through some grates, and then they get passed through a curved tube where we have the magnet, and the heavier the molecule, as I said, the harder it is to move using a magnet, and so it will move less. The lighter it is, it will move more and will bend more, and you've got a detector, which then you know based on the position it hits the detector what mass it is, or specifically what mass to charge it has. And the result that you get is a graph of these different mass to charge ratios and the relative abundance. So the more of that particular mass over charge, the higher the bar will appear. Now, how do we explain this? The electrons remove outer electrons from the molecule, creating positive ions. In many cases, all this will do is generate a positive ion of your full, complete molecule. And so that should be your heaviest m/z, is the full molecule as a positive ion. And we call this the molecular ion or the parent ion. And once you know the m/z, that tells you the GFM. And the parent ion or molecular ion is always your heaviest or your furthest peak to the right. So when you're looking at mass spec, the first thing you're doing is looking at the very right hand side of the graph. That's going to tell me the molecular ion and the GFM. So here we've got propanone, and there's an arrow for the molecule on the right hand side, so sorry, for the signal on the right hand side, telling you that is the molecular ion, and it's got an m/z of 58. And if you were to add up all the GFM of propanone, it's got 3 carbons, 1 oxygen, and 6 hydrogens. That adds up to give 58, so it does match. Now, remember, however, if you're asked what does the molecular ion show, remember it is an ion, and with mass spectrometry, everything's positively charged. So if you're asked to write down the formula of the molecular ion, it is the formula of the molecule with a positive charge, and we usually put square brackets around these things and then the positive charge. Now, as you saw from that spectrum, there wasn't just one signal, there were lots of other signals. And that is because when a molecule gets hit with these really high energy electrons, if they hit an electron that's involved within a bond, it can cause that bond to break and split the molecule into fragments. Each fragment will be parts of the original molecule, and typically areas that will easily be broken off would be branches, functional groups, and each one of those will have its own mass and therefore will appear at a unique and particular m/z, mass over charge ratio. So if we look again at our propanone, we see we've got a relatively proportional sized branch here at M over Z of 15, and that is your CH3 positive. Remember, it has to be positive. The next biggest one we can see is this one here at 43, and if we take off the CH3 from the molecule, and we just have this right hand side part, that is equal to 43. Another thing to notice as well is, see the molecular ion? It's not necessarily the most abundant fragment. We can see that actually there were more of those 43 M over Zs than there were the molecular ion. So don't look for the tallest one, it is for the heaviest one, the one furthest to the right for your molecular ion. And do not worry if some signals are higher than the molecular ion, that is normal. Now here are some common fragments, and again, remember, these are all positively charged. If you do not include the positive charge on anything related to mass spectrometry, you will lose the mark. And most questions are only worth 1 mark. So you'll have done all that detective work and lost it by not including just a positive charge. You must have the positive charge. So 15 is a CH3, 16 is an OH group, 29, not as common, that's an ethyl group, 45 is a really common one, that's carboxyl, 45. Now you don't necessarily have to remember these, but because these are really common, if you can at least remember the 15, the 16 and the 45, that really will help you because they're the most common fragments that will come up in mass spec questions. Now when it comes to mass spectrometry, isotopes can play a role, and they will affect the patterns, because if atoms exist as isotopes within one sample, even the molecular ion will have different versions, because you will have one isotope and another isotope, each forming within the full molecule. So a really good example to look at is chlorine. Chlorine has 2 isotopes, 35 and 37. When we look at its mass spectrum, we see 5 main signals. So we have one at 35, which is when the chlorine molecule has been split apart, and we're seeing the 35 atom on its own. We see one at 37, that is the 37 atom on its own. And then around the 70, we see 3 signals. So these are at 70, 72 and 74. The 71 is for 2 chlorine 35 together. The 72 is for a 35 and a 37. And then we've got the really small one, which is 74 for a 37 and a 37. The part on the left-hand side, 35 and 37, that actually is what you can use to work out the relative abundance of chlorine 35 and chlorine 37. There's much more 35 and 37, which then explains why, when we're looking at the molecular ions, that the one at 70 is the largest. So just be aware that when it comes to mass spectroscopy, if it is an element that definitely has isotopes, you will actually get a range of signals for the molecular ion. Now, often what you will do is you'll need to combine your microanalysis, that's where you've worked out the empirical formula, and your mass spectrometry, where you know the GFM, to allow you to then work out the chemical formula. So microanalysis tells you the empirical formula, mass spectrometry, gives you the GFM of the parent ion, and you can combine this information to give you the molecular or chemical formula. So for example, if a mass spectrum told you that the parent or the molecular ion had M over Z value of 88, and the microanalysis told you that the empirical formula was C2H4O, how could you use this to work out the overall chemical formula? Well, what you need to do is work out what is the mass of the empirical formula. So C2H4O, when we add that all together, it's 44. Now we can see that the parent ion, the full molecule, has a GFM of 88. So 2 empirical formulas fit into the GFM. So to work out the overall chemical formula, we just multiply all the values in the empirical formula by 2. So we now know that our molecular formula is C4HAO2. Had we just had microanalysis, we wouldn't know how many empirical formula units fitted into the molecule. Had we just got the mass spec, we would know the GFM, but we wouldn't be able to break that down into how many carbons, how many hydrogens, how many oxygens, etc. But by combining the 2 techniques together, we now have our final molecular formula, and that's going to be really useful at overall working out what compound we formed. So that has been our video on mass spectrometry.